Let's discuss solutions. A solution is a homogeneous mixture of two or more substances or components. Solutions may exist as gases, liquids, or solids. The solute is the substance being dissolved. It is the gas or solid being dissolved in a liquid. If it is of the same state, it is the component of lesser amount. The solvent is the substance doing the dissolving. In the case of a gas or solid being dissolved in a liquid, the solvent is the liquid. If it is of the same state, it is the component of greater amount. Example, coffee. The sugar in coffee you placed in the water to make your coffee is called the solute. The water itself is the solvent. Fluids that dissolve in each other in all proportions are said to be miscible fluids. Typically, when discussing solubility, the phrase like dissolves like is used. A more appropriate way of expressing this is to state that two substances with intermolecular forces of about the same type and magnitude are likely to be soluble in one another. For example, methanol and water are both polar with similar forces and magnitude. Therefore, they are miscible in each other. If two fluids do not mix, they are said to be immiscible. Example, oil, which is nonpolar, and water, which is polar. The layers separate with the less dense species on top. Oil in this case. Here's a picture showing you the oil and water where you have the two layers separated because one is polar and one's nonpolar, and the oil species will be on top because it is less dense. Here's an example of your methanol and water where they both are polar substances and they are miscible in each other. In most cases, like dissolves like. This means that polar solvents dissolve polar or ionic solutes, and nonpolar solvents dissolve nonpolar solids. The relative force of attraction of the solute for the solvent is a major factor in their solubility. The dipole-dipole interactions of water, being in a polar solvent, with a polar solute can be easily explained as electrostatic attractions between the delta minus and the delta plus between the dipoles and the molecules. Here's an example. You have your water molecules, which has delta pluses on the hydrogens and delta minus on the oxygen, and your polar solvent, which will have a delta minus and a delta plus. What occurs is an attraction between the hydrogen delta pluses and the delta minus of that polar solute, and then you have a attraction between the delta plus of the solute to that of the delta minus on the oxygen. Polar solvents such as water also interact well with ionic solutes because of the electrostatic attractions, that delta minus and delta plus between the cation and the anion with water. Example, you have a cation. There's an attraction between that cation and the oxygen on that water molecule because of that delta minus is attracted to that plus of the cation. For the anion, there's going to be an attraction between that negative charge on an anion and the hydrogens on the water because of that delta plus. Ionic compounds are the extreme in polarity. When water is a solvent, the attraction of ions to water molecules is referred to as hydration. Nonpolar solutes interact with nonpolar solvents primarily due to London forces. Heptane, C7H16, and octane, C8H18, are both nonpolar components of gasoline and are completely miscible liquids. However, for water, which is polar, to mix with gasoline, which is nonpolar, hydrogen bonds, which are very strong, must be broken and replaced with weaker London forces between water and gasoline. Here's a picture showing you B being gasoline and A being water. What happens is there's an attraction between the A molecules, which is very strong. That's the hydrogen bonding between the water molecules. And that is so strong that it actually pulls them together and separates them into two layers. Therefore, gasoline and water are immiscible because water has a stronger attraction for itself, stronger solvent-solvent interaction, causing the two substances to separate into the layers with the less dense gas on top. Solubility is the amount of solute that can dissolve in a given amount of solvent at given conditions. Many factors affect solubility, such as temperature. For most solids, if you increase the temperature, you're going to increase the solubility. There is a limit as to how much of a given solute will dissolve at a given temperature. A saturated solution is one holding as much solute as possible at a stated temperature. At 20 degrees C, the solubility of sodium chloride in water, its saturation point, is 36 grams of sodium chloride per 100 milliliters of water. What that basically means, if I was to take 30 grams of sodium chloride and dissolve it in water, I would have all the sodium chloride dissolved. That's an unsaturated solution. All 30 grams of sodium chloride is in the solution. Now say I added 40 grams to 100 milliliters of water. What we're saying here is we would have a saturated solution because I'm past that 36 grams that it can have. We have 36 grams of sodium chloride that will be dissolved in the water as aqueous ions, and then 4 grams of sodium chloride that will remain undissolved as a solid, either suspended in solution or precipitating down at the bottom of the flask. Sometimes it is possible to attain a supersaturated solution, that is, one that contains more solute than is possible at a given temperature. If we heat up a solution, we can increase the solubility and get more in solution. That's a supersaturated solution. However, supersaturated solutions are unstable, and the slightest disturbance, if you tap the beaker or you add one crystal to it, will cause an excess solute to crystallize out. Here's a picture of a crystallization from a supersaturated solution of sodium acetate. Homework 70.